In today's lesson, we're going to look at point estimation for the first time. The idea with point estimation is that we actually want to be able to come up with some estimate for the population parameter that we care about. So we've talked a lot about how in statistics our goal is to make inferences about something in a population when we can only view a sample. And so the question that we have today is, how can we take that sample and actually create some sort of estimate for the thing that we care about in the population in such a way that we know we're going to be getting something valuable? So that's the idea behind point estimation. Now, with today's lesson, we have several different goals here. So we want to be able to differentiate between estimators and estimates. Now, this is sort of a linguistic difference, but it's going to be important terminology for you to make sense of. We also want to understand how we're going to be evaluating point estimates. So we'll look at the mean square error, the bias, and the variance of an estimator. We want to describe what the MVUE is, or the minimum variance unbiased estimator. So in some sense, the MVUE is going to be the best estimator among a set of different estimators. And we want to define the standard error. Now, we saw the standard error very briefly in the last lesson when we were looking at the sampling distribution of the sample mean, but we want to define this sort of more broadly here. So to begin, I'm not sure if any of you have ever been to a children's birthday party where you play pin the tail on the donkey, but if you're not familiar with the game, the idea is you have a donkey, it's posted on the wall, you blindfold a child, you spin them around a bunch, you give them a tack with a tail on it, and then they have to try to stick that tack where the tail should go on the donkey. And then, inevitably, because they're dizzy and blindfolded, they don't stick it very close at all, and then, it's kind of a funny thing that you get to laugh at. And I think that this is actually kind of an intriguing way to think about what we're trying to do with point estimation, right? There's some parameter in the population that we want to know something about. And we don't have all of the information about that population, but we have some information, right? We know, roughly speaking, where it's going to be. And our goal is to come up with some number that's going to be as close as we possibly can, given the situation that we're in. And I think that's essentially what we're trying to do with pin the tail on the donkey as well, right? There's some true location, and we're trying to get as close as we can with a single pin, right? And this is a challenging thing to do because there's only one exact right location. And so our hope is that we can get close enough, that we can get into a region around what is actually true. And as we progress through the rest of the term, we're going to look at ways of actually sort of expanding out from getting only one single pin to being able to sort of lock down a whole region. But for now, we're thinking about, okay, we only get one option to pin onto this board. How can we make sure that we're doing the best that we can? So normally, we cannot learn information about populations through a census, right? This has been the central dilemma of this whole course. We don't normally get to take a full census, and so we have our samples. And so to make matters concrete, let's assume that theta is the parameter that we're interested in. So theta represents whatever the value in the population that we want to make inferences about. It could be the average height from a population. It could be the efficacy of a medical treatment. It could be the yield from chemical manufacturing. Right? Whatever theta represents is some number, and there's a true number out there, and we want to get as close as we can to saying something about theta. Now, we're not going to be able to actually measure theta directly, so we're going to take a sample, and we want to come up with some value from that sample that's going to be a good estimate for theta, and we're going to denote that with this theta hat notation. So anytime we want to estimate some parameter, if we draw a little hat above it, that's going to represent sort of our best attempt of using a sample to calculate what that parameter might actually be. Now, this single statistic that we're going to be computing is going to be some single underlying value computed based on the sample that we have, and we're hoping that it's going to be some sensible value. We hope that it's going to be close. We're hoping that, we're not at the party pinning the tail on the head of the donkey and having all of our friends laugh at us, right? We're hoping that we're going to get close to what's actually happening. So we're going to refer to that single value as a point estimate. Sometimes we'll just say estimate, but if we want to be very specific, we'll call it a point estimate. And the whole sort of purpose here is to figure out, is that estimate going to be good or not? Now, in order to actually derive that estimate, right, once we have a sample and we apply the procedure we're going to be using, we get some value. But before we've actually applied that procedure, we have to decide on what is that procedure, right? And that procedure itself is going to be some mathematical function. So you could think about, say, the sample mean, right? Of course, you can compute the sample mean once you have a data set, but we can also write down just as a mathematical function that the sample mean is going to be 1 over n times by the sum of all of the data points. And when you express it that way, it's just a function of data that we've not yet collected. And when we're talking about that function, and we're not talking about a specific value that that function outputs, we're going to call that an estimator. Okay, so the estimator is the underlying function. When we actually plug data into the estimator, it's going to output some single value. We call that single value an estimate. So estimators produce estimates. I really want to emphasize this point here because this terminology can get very confusing, but it doesn't need to be. I don't think so. So estimates are going to be single values. Estimators are functions. Now, they're functions of random variables. They take in those capital letters that we've been talking about. And because they're functions of random variables, estimators themselves are random variables, right? The sample mean before you have a sample is going to be a random variable. We already talked about what its distribution is going to look like. This is true in general, right? If you think about just summing up all of your data, well, until you've collected data, that's going to be a random quantity. You can think about taking the square root of the maximum value. That's going to be random until you have data to actually compute it with. So the estimators are those random functions. They're random variables themselves. Anytime that we actually use the estimator, we're producing an estimate. So if you actually take the square root of the maximum value in a data set, that's going to be an estimate for that value. Before you've actually collected the data and gotten a number out, it's an estimator. We can think about an estimate as being an observation from the estimator random variable, right? In the same way that we thought about x, capital X being a random variable and lowercase x being an observation, the estimate is going to be our observation from the estimator, right? So you can think about estimates as being drawn from their sampling distribution. And so if you knew that the sampling distribution was normal, then the estimates are going to be realizations of a normal distribution. Now, there's going to typically be many different estimators for any parameter of interest. There's going to be many different functions that will allow us to produce estimates about the function or about the parameter of interest. And the estimate that we produce is going to depend both on what's the estimator that we're using and also what is the data that we've actually collected, right? So the estimator is just about the procedure. The estimate's going to depend both on that procedure as well as on the actual data that we've ended up collecting, okay? And so if you thought about, say, the normal distribution, we know that the normal distribution is symmetric. We know that the median of the normal distribution is going to fall exactly on top of the mean, right? And so we could think about taking, if we wanted to estimate where is the center of this distribution, we could think about using either the mean or the median as our estimator. And depending on the data that you've collected, the mean and the median are going to typically be different. And then if you collect different data, they're both going to be different as well, right? And so we have to decide on our procedure, and then we have to collect our data, and that's going to define what ends up happening with our estimate. Now, because the estimates are going to depend on the data and on the procedure, we can't always be sure that our estimates are going to be close. However, we do get to control which procedure we're using. We get to control the estimator that we select. We don't get to control what data we end up with, right? That's going to be random. But because we get to pick the estimator, what we can do is study the behavior of the estimator as a whole, right? And if the estimator is likely to behave well, then it's going to be a good estimator. And we can be really sure that when we get a sample, the estimate that we produce with it is going to behave well as well, right? And so we can say that some estimators are going to be better than other estimators. Now, on average, a good estimator should be close to the truth, right? I think we can all agree on that we want the estimator itself to typically produce results that are close to the true population value. And one way that we could measure this is by using the mean square error, or the MSE, right? So the MSE is given by this equation here, and it looks a little bit like the variance, right? So we take theta hat, which is our estimator, we subtract off theta, which is the true value, we square it, and then we take the expected value. And remember that we're taking the expected value here because theta hat is going to be a random variable, right? Theta is just some constant, theta hat's the random variable. And so this looks very similar to the variance, but in general, it's not going to be exactly equal to the variance, right? Instead, what we're going to be able to say is that it's going to be decomposable into what we would call the bias term, as well as into the variance term, right? So we can look a little bit more into what those terms actually are. So the bias of an estimator is how far it is expected to be from its true value, right? So if we were to take the expected value of theta hat minus theta, this is going to be the bias of the estimator here. And so whenever the estimator has the same expectation as the true value, we're going to say that it's unbiased because this expression is going to be 0. But in general, we can't say that it's always going to be the case that the expected value of our estimator is equal to the true value, right? So if an estimator has the expected value of theta hat equals theta, we say that it's unbiased, right? So there is no bias in that term, or the bias is equal to 0. And generally, we're going to prefer a smaller bias, right? So if we think about what we're saying, the bias is measuring how far we expect to be away from the right value. And so on average, if we want to be close to the true value, we want our bias to be small. Everything else equal, we would prefer our estimators to be unbiased. We would prefer this value to be 0 if everything else were held to be exactly the same. Now, to make a concrete example, this is why most people divide by n-1 rather than n when they're computing the sample variance, okay? And so I will make a point here that says that unbiasedness is not normally carried through functions. I'll point this out on the next slide when we're actually talking about the sample variance directly. But just to say that if your sample variance is unbiased, that doesn't mean that if you take the square root, it's going to stay unbiased. So I'll discuss that more in a second here. And there's also going to be the fact that some estimators are going to be unbiased when n goes to infinity, and those are said to be asymptotically unbiased. So we'll take a look at all of these sort of more concretely in a second here. When we introduced the sample variance, we defined this to be the sum of the squared deviations divided by n, right? And at that point, I said to you, this isn't the formula you're normally going to see. Ignore that for now, right? And the reason this isn't the formula that you're normally going to see is because this formula is actually biased, okay? If you take the expected value of this expression, you're not going to find that this equals exactly sigma squared, okay? And so it's more common for you to see that the sample variance is defined to be this squared deviations divided by n-1. And the reason that we divide by n-1 is because this is going to be unbiased. If you take the expected value of this second s squared term here, that's going to exactly equal sigma squared. But if you do it of the first term, it's not going to exactly equal. Now, some points to make. If you were to then take the square root here, as we were just saying, the square root's not going to be unbiased for the standard deviation of the distribution, or at least not in general, right? So biasness does not translate through functions, right? And so we typically care more about the variance than about the standard deviation. And so if we have an unbiased estimator for the variance, that's all that we care about. The other point that I'll make is about asymptotically unbiased estimators, right? If n is really big, whether you're dividing by n or by n minus 1 doesn't make any difference, right? If you divide by 1,000,000 or you divide by 999,999, it's the same thing. And so as n gets bigger and bigger, the bias that's in our first estimator here is going to shrink towards 0, right? It's never going to be truly unbiased, but it's going to behave as though it's unbiased, right? And so what we see here is that this modified variance estimator is unbiased. If you apply functions to it, it's not going to stay unbiased. But there are other estimators, like the one that we've been using up until now, that if the sample size is large enough, will behave as though they're unbiased. Now, going forward in this class, we're going to start using this as the sample variance estimator. We're going to start dividing by n minus 1 instead of by n, right? So up until now, we've divided by n. That's been fine. But going forward, we're going to divide by n minus 1 instead. It's not going to make a big difference, but just know that this is what is expected going forward. Now, consider that both x bar and x1 are going to be unbiased for the sample or for the mean of the distribution. Right? The expected value of x bar we saw in our last lecture is going to be exactly the expected value of x, and the first value in our sample is going to have expected value x as well. And so because they're both unbiased for the sample mean, or for the population mean rather, we can say that unbiasedness alone is not going to be sufficient for a good estimator, right? We can't simply say that anything that's unbiased is going to be good, because of course, if we wanted to know what is the overall average in a population, taking a sample of size 1 and just recording that value is obviously not going to be as good as taking a sample of size 100 and taking the average there, right? We just know that to be the truth. And so unbiasedness is not capturing everything. And so instead of just thinking about the bias, that's where we're going to think about the variance as well. So we define the variance of an estimator in the same way as we define the variance for any other random variable. We take the expected value of theta hat minus the expected value of theta hat squared. Okay? Now, I'll point out again, this is not the same formula as we saw for the MSE. Within the MSE, what we're subtracting off is going to be theta. And unless the estimator is unbiased, expected value of theta hat does not equal theta. Right? So this is just our standard variance formula. The MSE plugs in theta instead. When we have zero bias, then the variance and MSE will be equal to one another. Oftentimes, we're going to restrict our focus to only the unbiased estimators, right? We're going to say, we don't want any estimator that's going to be biased at all, so let's only look at unbiased estimators. And then in that case, we can simply minimize the variance of our estimators, find the estimator that gives us the lowest variance, and we can call that one to be the best unbiased estimator. We refer to this as the minimum variance unbiased estimator, or the MVUE, right? And so if we think about what does the MVUE say? Well, it's going to be the estimator, which is unbiased, that has the minimum variance, right? So it's sort of a self-descriptive name, which is nice. But in some sense, the MVUE is going to be the best estimator if we're only going to consider estimators that are unbiased. So in terms of the properties of the MVUE is going to be the unbiased estimator that has the smallest possible variance. This is going to depend both on the underlying population distribution and on what parameter we're actually estimating. Okay. And so it's not always going to be obvious what the MVUE is. In fact, generally speaking, it's not going to be obvious. These are typically hard to find, but both of those things are going to matter here. Now, in some of the problems that we've considered, we actually know what the MVUE is. And so perhaps the most illustrative example is that in normal populations, if we want to estimate the mean, then the sample mean is going to be the minimum variance unbiased estimator. If we have binomial populations and we want to estimate the probability of success, then p hat, which is the sample proportion, is going to be the MVUE. In general, the sample mean is not going to be the MVUE for the population mean. These are two special cases that we've seen where in this sense, these are going to be sort of the best available estimator. But generally speaking, the sample mean is not going to be the best possible estimator. If an estimator is robust, then it performs well in many distributions, right? And we've talked about using the sample mean a lot. It does get used quite a lot in practice, and some of the reason it gets used in practice is because of the central limit theorem that we saw before. But generally speaking, the mean's actually not a very robust estimator. It doesn't behave nearly as well as other estimators that we have for all distributions. However, there's a lot of important cases where it does perform very well. So in particular, normal populations and binomial populations. And so because of this, we're going to keep looking at the sample mean. But I'll just point out that the sample mean is only optimal in sort of select situations. Now, onto the standard error. We defined what the standard error was in terms of the sample mean, but we can just broaden that to talk about the standard error of any estimator. So the standard error of an estimator is just the standard deviation of that estimator. So we denote this with this SE of theta hat, and it's going to be the square root of the variance of theta hat. The standard error is often going to rely on parameters from the distribution that we don't know, and so often we're going to have to estimate the standard error instead. Sometimes we can find good analytical expressions to estimate the standard error. Other times we're going to have to use sort of more advanced strategies, such as, say, the bootstrap. We're not going to actually look at the bootstrap in this course specifically, but just know that the standard error relies on being able to compute this variance. The variance is often going to depend on parameters that we don't know, and so we'll have to find other ways of estimating that. Now, the reason that we're bringing up the standard error is that anytime you report a point estimate, you should also always report the standard error. This is true far beyond this course, but the idea is if you're reporting a standard error, you're reporting some sense of how confident are you in this value that you've just estimated, right? And so instead of just relying on, say, pinning that tail on the donkey, you get to say, not only here's the estimate, but we're not very sure that we got close. Or hopefully you can say, look how small our standard error is. Therefore, we're very confident that the true value is going to be concentrated around the point estimate we're giving, right? And so the standard error, only the square root of the variance, but we should always be reporting it to try to quantify how uncertain we are. So that was a lot to cover. To give a quick rundown of what we just saw, estimates are going to be single values that represent sort of our guess as to what a population parameter actually is. Estimators are random variables, and they produce values which we call estimates. Estimators are assessed through their MSE. The MSE can be broken down into the bias squared plus the variance, right? We saw that the bias is the difference between the expected value of the estimator and their true value. And if the bias is equal to 0, then we say that it is an unbiased estimator. In general, we prefer unbiased estimators, but it's not always going to be the case. And if we only look at unbiased estimators, then the MVUE is the best unbiased estimator. It's the minimal variance unbiased estimator. Standard errors quantify our uncertainty in our point estimates, and as a result, they should always be reported. And the standard error is just going to be the square root of the variance of an estimator. So I recognize that that was definitely a lot to digest. Over the coming lessons, we'll actually start looking at some of these topics in a little bit more depth, and we'll sort of start to consider why we care about them. So hopefully between reviewing what we've just covered, trying out some of the questions, and then seeing what we start talking about in the coming lessons, all of this makes sense. But of course, if you have any questions, do please let me know. And in the meantime, I hope to see you all in the next lesson.